General and generalized linear models. We're going to talk about four major types of things. We're going to start with some new tidyverse-oriented stuff. We're going to talk about correlations and covariance, and matrices in particular. Then we're going to talk about linear model and the generalized linear model functions in R. There'll be a lot like last time, a lot like the ANOVA content, where we're going to cover that content and then add some stuff to it to give you kind of a broad range of tools in the event that you need to use these types of regressions on your own. We'll be looking at stepwise and all subsets regression, for example. We'll be doing model comparisons if you're doing hierarchical modeling. Things like looking for moderators, you need to know how to compare 2R squareds. And we'll look at relative importance modeling very briefly. And then finally, we're going to cover some more McGritter at the very end. So, first, a little bit of new tidyverse. I wanted to introduce this idea because we're starting to get to the point where we're working with more data sets. You're going to start to do more operations of the type that we traditionally do in psychology. And one of the things that you might want to do is calculate a mean of multiple variables. That is not as straightforward a thing as you might think because of the way that R handles computations. And it is a little trickier than just saying new variable equals mean of other variables. The reason for that is because remember that the mean command actually takes an input of variables in general. So if you say mean of variable name, what it's going to do is take every value within that variable name for every case and calculate a mean. So you've used it that way. If you do mean, data set $ variable name, you'll get one number. But that's not what you want. You actually want one number per person, which is a very different operation. So to do that, you actually have to wrap. You can do it in base R, but it's a little complicated. I like the dplyr version of it better. You can do it by wrapping your command in this guy right here called Rowwise, which actually rotates certain operations within a mutate command or a transmute command so that they operate on a row-wise basis. To illustrate why that's important, let me show you. I'm going to use this data set for a lot of demonstrations today. It comes from the BFI data set, which comes within the psych library, but a modification of it. I'm going to comment out Rowwise, and we're going to see what this does. So what I've done in this basic command right here, I've taken the BFI data set, and if you're not familiar with the BFI data set, I will show it to you very briefly. BFI data set is essentially a big five inventory measure. We have 5 items for each of the big 5 across 2,800 observations, as well as gender, education, and age covariates. So I'm just trying to say, well, you know what? We probably don't want to work with the individual items in our data set. We want to have mean scores for each of these. So we need to calculate means. And you might intuitively do this without that Rowwise command. But if we look over here, you will notice, well, number one, that I have all NAs. The reason for that is because in the mean command, remember, it automatically, if it finds any missing values, returns a missing value. So this means we have missing values kind of everywhere. We're going to add an na.rm equals true to each of these to get around that error, and then you will still see there's a problem. Now that does not look like a data set containing unique means for each individual, does it? Because what you've really done here in creating these values, you notice they're all the same, is that this command says, well, take the mean of all values of O1, all values of O2, all values of O3, all values of O4, all values of O5. So that's really, that number you're seeing for O is the average score across items 1 through 5 across every participant in the data set, not for any individual person. So in order to get around that, we use this Rowwise command in the pipe. And when I run that, you will see that all of the scores have now changed. So if you need to calculate mean scores by variable, this is the easiest way to do it. There are ways to do it with base R. I wouldn't recommend any of them. And there's also ways to do it using some of the tools in the psych package. We'll revisit that toward the end of the course because there's certain situations where that's easier, mostly involving weighting. But for most purposes, if you're just trying to say, you know what, I need a mean of 4 items per person, then Rowwise is the way to do it. You're also, however, going to want to pipe this into one more command called ungroup. Ungroup does what you would expect it to do. It removes grouping variables. What Rowwise does specifically is not really well documented, and it can affect other things later in the pipe in unexpected ways. It sometimes screws with ggplot, for example, because it basically, the same way that we use group by to define groups by like variables, this essentially defines a group by row number. So every row is a group. So it's kind of weird under the hood. So all that means is anytime you use Rowwise, after you finish doing your transformation, after you finish creating your new mean variables, just throw an ungroup at the end. That's all. So that process, and you can actually, I'll show you what that looks like more specifically. If I go down here, you will also see that when I have Rowwise on, it adds an extra class. So when I use Rowwise, it becomes this Rowwise underscore df as well as a tibble, and Rowwise dfs behave differently. But you can get rid of that by ungrouping and you go back to a standard tibble. Okay, that makes sense? So anytime that you need to calculate these, all that means is go Rowwise, create your scale means, and then ungroup immediately. That's all you have to do every time you want to do that. And you'll need that for this week's project. Okay. So yeah, that's our first little bit. That's actually dplyr more so than tidyverse, but it's, than tidyverse than dplyr is. And you will see that, you'll see that in the project, and I'm also going to be working with this particular data set for the examples today. Okay, correlations and covariances. This is real easy. There are two basic ways to do correlations and covariances. One is to give an entire data frame. Two is to give two specific variables that you want to calculate one between. You can use either core or COV. COV will give you the covariance matrix, of course, just unstandardized correlations, or core will give you the correlations. Importantly, things you should remember about this: if you give it a full data frame, they all have to be numeric. So if there is any factor variable in your matrix, then that command will just fail. It will just throw you an error. It will say something like x is non-numeric, but it won't tell you which x it's talking about. The reason is because you have to subset before you get to this point. So if you want to throw into a correlation, you probably are going to do something like this to create a matrix. In tidyverse, doing a data frame into a select for whatever it is you want a matrix for, and then core. Just pipe it right in. The next simplest way to do it is this way, by actually giving the variables themselves. You've done that many weeks ago. You may or may not remember. But what you do in this format, if you're not in tidyverse, is you can say, for example, core parentheses df $ variable name, comma df $ variable name, to get the correlation between any two random things that you want to get correlation between. So, for example, in our myBFI dataset, I could do core myBFI O versus myBFI A. I'm going to say na.rm equals true. Actually, I can't do an equal there. Oh, no, that's right. Can't do na.rm at all. This is the other piece of this that's important. The way that you handle NAs behaves differently depending on what you want the matrix to do. There are multiple types of missing values handling algorithms included in these two cores, in core and cov. If you use complete.obs, that's listwise, and pairwise.complete.obs, that's pairwise deletion. There's actually a few more, though. If you look at the help file associated with core, you will see all of the different types right here, and there's full definitions later. You will see me abbreviate these sometimes. Instead of typing out, for example, complete, I may just write comp or complete. And for pairwise.complete.obs, I may just write pair or pairwise. It doesn't matter. Because as long as you have the first part, that it will figure out what you mean. So if I go back to here, and instead of na.rm, I'm going to go use equals complete, then we can get the correlation there. And in this case, if I did complete or if I did pairwise, I get the same answer because there's only one correlation. So it only matters if you have, like say for example, we want to do the entire correlation matrix. If I want to do core myBFI, number one, this probably won't work. Whoop, not cough. Oh, no. Gender, I haven't converted gender to a factor, so it did work. So here we get our full correlation matrix with our default handling. If I change our use command into pairwise, it might, actually, I'm not sure what it's defaulting to right now. It might be defaulting to pairwise. Actually, those look the same, don't they? Well, I'm not sure why that works with one and not the other. That's interesting. I'll have to investigate that too. Anyway, this command forces your specific missing value handling. It seems to behave differently with data frames, which I did not realize until just now. But if you want to get alternative correlation types, you can also use this guy right here for method. If I do method equals spearman, or method equals spearman, then we get a Spearman's row, and you can get Kendall's tau the same way if you use a Kendall in that same place. So, yeah. You can also pipe all of this into APA tables and spit out a correlation matrix that way. APA tables actually has some really neat kind of functions to it for correlation matrices. If I do APA core.table, my BFI, and let me spit this out to... let me define a working directory real quick. I'm going to go to the desktop. I'm going to call this sample.doc. Then if I go look at that file, you will see that I get not only a correlation matrix, but I actually get confidence intervals associated with each of the correlations, as well as your standard star notation for statistical significance and a full note. So for basic correlation tables, apa.core.table is very handy. You can also, there are options to suppress the confidence intervals if you don't want them, and there's also options to suppress the stars if you don't want them. But otherwise, yeah, it gives you a nice convenient descriptives plus correlation table of the type that we commonly see in our journals. So, yeah, that's a basic idea on correlations and covariances, and that's basically all you need from them. The general linear model is where we're going to spend most of our time. LM is, we already used it a little bit when we were talking about the ANOVA material, except now, of course, we don't need sums of squares and whatnot from the ANOVA type. So now we're going to generalize. There are a bunch of functions that will work on any given LM. So once you do LM and give it a formula, you have what you would call a model object, an LM object. And all of these commands where you see LM after them will work on that model object. So if I kick back over here, not that one. If I kick back over RStudio, and I create a model, and I'm going to say linear model, what do we want to do? Let's predict O from the others. Using data, my BFI. If I just type model, I get very little information about that model. However, I can type summary model, and I get the full table of your kind of traditional weights table, as well as standard errors and R-squared information, as well as your overall model F, if you care about that kind of thing. I can also instead do COF. COF will give me all the individual model pieces conveniently in one set, where I can use them in other pieces. If you take a look at Glimpse for any of these, they'll tell you what the types are, which can be important if you're trying to find it. In this case, COF, the reason that you might want that is because it actually just gives you a 5-item vector. So you can actually just refer to it as a vector. You don't have to hunt around in this thing, which can be a little bit tricky. If I look at a model, for example, you'll see that I have a pretty complex hierarchical structure of elements to this model, where if I wanted to extract any particular piece of it, I would need to figure out where it is. Sometimes you have to do that. Sometimes you will need to get specific numbers from a model and put them into another analysis. Don't copy-paste things, not a good practice. Instead, you have to figure out how to refer to it. If I, for example, wanted to get at let's see, what would be a good thing to grab? Actually, I'm going to grab it out of the summary instead. I'm going to show you what this one looks like, because it's a little different too. So in this one, you can see at the end, I've added a bunch of statistics. The thing I really want is the R-squared. So I'm going to save this into summary model gets this. And then I'm going to say summary model $, and we can pull out, for example, the R-squared, right, as a single value. So that's how you would identify that process that I just showed you. You basically glimpse the object, figure out where all the stuff is, and then use $ notation to try to work your way down into the thing you need. So if you need an R squared, which you will for something we'll do later today, then you have to figure out where it is using those terms. Okay? Does that make sense? Don't ever be afraid to save some kind of output to a variable and then just look around in it. Like, poking around in variables is a very common practice during code development. Number one, never copy paste. Really good general rule. And number two, just save it to an object and look around using glimpse or using the RStudio interface. If you notice that when I hit the $, I got that nice convenient little pop-up that showed me all the other things in there. You can also use that hierarchically. Let's see if I did it on model and then coefficients. What do we get there? Yeah. Actually, it's not hierarchical in model. Anyway, if it is, if you do have hierarchical objects, and I guess I don't have any here. No, I don't. So if you have hierarchical objects where you have one object stored inside another object, you can keep pressing $. That's all the thing I was trying to demonstrate. So if you write a variable named $, find the next thing you want, and then press another $, it will actually keep prompting you for subunits, sub-items within the object. So that's useful. Fitted is another thing we can put on models. Fitted values just gives all of your fitted values. In ordinary least squares linear regression, that and, not please, predict are going to be the same, because what you're basically doing is taking the regression line, taking every value within the data frame, or every case within the data frame, and then plugging in those values as input to the model. So fitted and predict are going to give you the same answers for OLS regression. If you're doing logistic, or actually if you're doing anything with a link function, so you looked at link functions in the data camp material. Anything with a link function where you're doing logistic, or you're doing some weird type of Gaussian, or you're doing any other type of distribution, then the fitted values and the predicted values won't be the same, because we have the transformations between the two. But for OLS, they're the same. You can also predict from a new data frame. This I felt like wasn't real clear as to what you were actually doing with the predict command, so let me just be a little clearer. What predict does, if you give it this kind of notation, is it's going to take your existing linear model, and in this case I already defined it as model, so I'll just type that there. And in the second one, let's call it new data, what it's going to do is look for a data frame that has these names. So in my model, I have O as a function of C, E, A, and N, right? That's the formula I used in the ln command. Let me go back to that real quick. This formula. So right now I have O is being regressed on C, E, A, and N. That means that if I want to predict new values from new data, I could use this command, and that new data would need to be a data frame that contained 4 variables, C, E, A, and N. Okay? So that's all it means. So if you use the predict command, you can actually get a brand new data frame, and for the I/O folks, this is really important when you're doing selection work. Like if you're trying to take an existing selection formula and throw in like new cases to predict their job performance. This is where you would do it. You would get a new data frame here, and you would throw it into the model using the predict command. But all that does, from a technical perspective, is it basically goes line by line and creates y-hats, or predicted values, on the basis of the 4 variables that you've been given. So you could use that, for example, to within a pipe, to take a data frame that doesn't contain predicted values and then use mutate predict to add a new column of predicted values. So that's the way that you would use that in practice. Okay. Then we have tidy and augment. Tidy we used last time as a way to just very conveniently get some better looking information. I'm going to use, look this on, I need broom. Whoops. Library broom. Tidy basically just takes whatever the output is and then flips it in order to turn it into a data frame. You can actually get a sense of what tidy's really doing if you keep layering tidies in. You can tidy, and then you start to see how it's like, it's continuously reorganizing, restructuring the model every time. Everything that's in tidy you could actually do yourself in a not terribly convoluted code, but it's definitely more work than just typing tidy. So tidy is a really useful function for getting back some basic information about any more complicated object. That's different from augment. Augment is specifically designed to tidy but also add useful extra information that is not included in the main thing that's being rotated. So if I augment, you will see, for example, here, that we can't deal with a summary because summaries are not what augment is designed to handle, but we can augment a model. Actually, I'm going to look at the head of augment. In order to pull out all of the data set that's involved in the model, your fitted values, your residuals, your Cook's distances, and your standardized residuals. And we usually don't actually look at raw leverages, but they're there too if you need them. All of that is contained within augment. So if you want to do something with those values, you can. The major use for that is this fitted line, the actual predicted values, because that's how you would normally generate unique graphs. Because if you wanted to use these fitted values given particular inputs on a figure, then this is where you get them. So that's going to be the major use. And I'll show you an example of that in just a few minutes. So yeah, tidy and augment, useful for this. A function you might or might not need, depending on what you like to do with your regressions, is using the quant_psych library. Pay attention to those capitalizations. I'm going to do library quant_psych. Is lm.beta. Now, if I look for the coefficients associated with my model, you should interpret these as what SPSS would call a B, which means that these are actual regression weights. If instead what you need is standardized weights, then you can use lm.beta to standardize them. That's the only thing out of quant_psych you need, and that's all it does. It's actually a very simple formula. You could do it yourself if you really wanted to. You can actually see what it does if you type in lm.beta. It's basically just taking the coefficients and it's systematically rescaling them by the standard deviations, just like you would if you were calculating your own standardized coefficients. But this just does it all in one step, so you don't have to worry about doing the math yourself. So that's useful if you want to use standardized coefficients for some reason, which of course vary of an appropriateness based on the context. Not a stats class, not going to go into it. Okay, so standardized coefficients if you want them right there. Plots, really important in the context of linear modeling. We did this already with ANOVA. They're the same plots that they were last time. I've given you a little bit of hints as to what their purpose is, as well as a link to a website that you might find useful if you've forgotten. If it's been a while. Residual versus fitted plots, scale location plots, normality, quantile plots, and residual versus leverage plots. All four of those can be put into a single figure by using this command right here. So I'm going to demonstrate what this is. This par, all right, number one, we're going into base R graphics for a minute. So it's going to be weirdly convoluted. What par does is it actually it's a graphical parameter. It's the way you set graphical parameters. And what it does is it sort of sets an under the hood option for R to say, for all figures I'm about to make, apply these options. Okay? So what mfro does is puts multiple figures per row and column based on this specification. So when I run this command, when I do par mfro equals 2 and 2, you will see absolutely nothing change, because what has happened is it says now for any base R figures we create in the future, use this option. To see why that's useful, I can say I do plot model. Instead of creating 4 plots, that's now going to create this single plot that you can use all in one place, a convenient thing to show an advisor, a co-author, etc. When you're trying to talk about regression diagnostics. You can see in this case, we've got a little bit of leverage going on in a few cases. This is a little bit curvilinear, might be a concern. That's not too bad. And QQ looks okay. Slight bend to the tails, but that's very common. I was taught that these two are called hamburger plots when I was in grad school, because in general they should look kind of like a hamburger, thicker in the middle and taper off to the sides. which is one of the few things that I remember from that regression class. So these two plots show what we're looking for: straight line for the QQ and kind of a flat line for the leverage plot. It also helpfully gives you, of course, these individual case ID numbers here if you want them. These actually are case IDs, so if you subset by row, that's the number you subset on. So if I did, for example, my BFI and I want row 1430, then we get that value out of there. We're going to look at, what do we look at? Oh, par. So the downside of using par is that when we have this setting, it keeps applying forever. So if right now I created a QQ plot, I would actually create a 2x2 matrix of QQ plots, which is really not ever what you want to do with, not QQ plot, GG plot, sorry. If I made a GG plot right now, I would create a 2x2 matrix of GG plots, which is not what I want. So I actually have to reset this by going back and specifying this back down to 1, 1. And again, it won't look like it did anything, but it did. You can check it for yourself if you replot your model. You will find it goes back to your individual press return to see each individual new plot. Okay. So that's just a convenient thing that you can do. That way you can also save your assumptions plots as a file if you wanted to, like save it as a PNG or a GIF or whatever. And then you have all your assumption checking saved where you can look all in one place. Okay. So the car package is next. A lot of things that you just might want. We're not going to really step through them. I just want you to be aware that this kind of thing exists in that plot. We have leverage plots. We have added variable plots, also called partial regression plots, that you can get from these two commands. These two will actually run specific statistical tests. This will give you the most extreme residual in your data set and look at a Bonferroni corrected p-value to see if you have any outliers, because if your most extreme is outlying, then you have outliers. So that could be a quick test of that. NCV is non-constant variance test if you want to do tests for homoscedasticity. VIF will calculate your variance inflation factors to look at multicollinearity. Lots of standards associated with VIF, by the way, if you pay attention to VIF. And there's things like any values over 10, or any values over the square root of that value over 2, or any values over 50, or any values over 3, 4. There's all sorts of different standards because there's absolutely no real rational way to do it. What I would recommend, though, if you are looking at multicollinearity, just see if the numbers look high. Like, is it more than 2? Then look into it, and maybe it's a problem and maybe it's not. All right, so those are your basic kind of assumptions tests on linear models. The two major classes of linear model, general linear model that you looked at in the data camp were parallel slopes models, which is kind of like an ANCOVA, and interactive models where you have multiple variables. All this formula notation is the same. Like nothing's changed from the ANOVA context. We can still use the colon to indicate explicit interactions, or we can use star to indicate implied interactions. These two are identical. They're the same command. Where things get a little bit different, and this was covered in data camp, but I wanted to call attention to it, is if you just give it variable names, if you just give ggplot variables like this is kind of the intuitive way to do it, like assign an x, assign a y, assign a moderator of your second x, and then create a linear regression smooth line, this will always draw the interaction, like every time, because there is one. So what ggplot does is it will sort of decompose your model into all of your parts by group, and then just create an individual regression for each one and then graph that value. So that means it basically ignores any of your specifications. Like there's no model here. It's just literally take these values, make a regression, take these values, make a regression, take these values. So you always see an interactive effect if you do this. If you don't want to do that, that's when you have to use the fitted values from augment. So in this example, I've used augment on a model that was a parallel slopes model, and then I have added in the fitted as the y element of geom line, but I have created the graph on the scale of the original y. So we have time to go through an example. So right now I have let me create a new model. Let's say we have O on, let's make it more interesting, A on N plus gender with data equals my BFI. Okay. So now you have a basic model. We can do our summary of our model. This is kind of your basic parallel slopes model. If I graph this the way that I would intuitively graph this, if I do ggplot of my BFI with an aesthetic of x is, where did I go? N. Our y is A, and color and group are going to be gender. And I'm going to add a geom smooth of type linear model. Boop. It is hard to see a little bit, but these are actually very slightly different lines. You can see this one actually tilts just a little bit up in comparison to this one. So if what you had, because what this has done is I haven't given it a model here. It's literally just taking all the data and drawing lines. So that means if there's an interaction of any magnitude, it's going to be there. So if you want a parallel slopes model, that means you have to manually go in and say, I don't want that interaction. The way that you do that is by fitting a parallel slopes model and then feeding it into ggplot. So instead of my BFI, I would do augment of model, and then instead of geom smooth, I do geom line, and for the aesthetic, I'm going to put in the new fitted values. So I typed that wrong. Here we go. And now we get a fully realized parallel slopes model. Okay. And if you wanted to add the error cloud around it, then you would just have to add a new geometry for that error cloud based on the other values in augment, if you wanted to put the standard error around it, because it just doesn't come by default. So that's it. So if you want to do that, that's the difference, and hopefully you saw how I modified one to get to the other. I'm just taking, instead of the raw data, which will always have all possible interactions because it's the raw data, then instead I took the results of the model specifically. You can extend that technique to anything. Any random thing that you want to create a figure of, that's usually how you do it. If you can't figure out how ggplot will do it natively, like using the geom smooth, if it's more complicated than that, then just get the fitted values and draw them directly. That is, by a good margin, the easiest way to do it. Okay. Yeah, that's your basic figuring. Okay, stepwise. Let me start by saying you should never use stepwise. But if you do want to use stepwise, you can find it using step AIC, which is in, I actually didn't write it in. It is in, I think it's in matrix models library. Actually, not quite sure. Doesn't matter, you're not going to use it, don't use it. But if you did, you can do forward, backward, and both ways regression using that command. If you do want to use stepwise, you actually want to use all subsets regression, which is different. All subsets regression is basically looking at every possible stepwise ordering simultaneously and then looking at the trade-offs between model fit and model complexity. It's a parsimony R² trade-off. And then graph them all together. You can do these, and I'll show you one in just a second, by using two different commands from two different libraries, leaps and car. And again, the situation you would do this in is, say you were in a practical setting and you had starter data, you had already collected data, you had like, I don't know, you did 20 or 30 scales because you had a big, huge amount of funding or time, and you got a whole bunch of people do a whole bunch of scales. And then somebody came in and said later, oh, hey, we can't afford that. You need to run like 5. Which 5 should be the best? Well, that's where all subsets is best. Don't use stepwise because stepwise is very biased by a lot of things. There's a lot of reasons stepwise is bad. But all subsets will actually give you that information yourself that you can take a look at. I'm going to use the car library. I'm going to use the leaps library. So what I'm going to do is create an all subsets model. Not going to call it that. Subsets model. All subsets model with reg subsets. And let's see, what are we going to do? O plus CAN, maybe? Or on CEAN. Yeah. In best will give you the 10 best subsets, and we're going to use data, or 10 best subsets within. And you can read it later if you want to with question mark reg subsets. If you've never done, did you do all subsets in class at all? In like the regression class? No? Oh, great. So if you want to do this kind of thing, you definitely want to read this before you get into it. It is really for the situations where you already have a study you've done and you have too many predictors. You need to do a new study, but you can't use that many, but you still need prediction to be as good as it can be. For subsets model, if we do this, you'll actually see all of the possible subsets that it is investigating in a matrix format. And the most interesting thing, though, you can do is subsets. And I call this subsets model statistic equals R squared. So what this has done is actually shows you for the different model combinations, which is the subset size, what is your R squared for each possible model. So you can see the CEAN, all variable model is obviously the best here, but you have a slight sacrifice in R squared, only looks like about 0.1 for all of these 3-parameter models here. That's more informative when you have like 20 or 30 or more variables. But you can see with this simple model the kind of information all subsets will give you. So it will actually go through and create optimized models based on all these patterns. And you can see even the zero order correlations down there at the bottom because we had enough subsets that every possible model combination is a subset. So they're all here. But this will give you that kind of practical information. Not a thing you would do for a paper, but in the real world, this is a kind of a common problem. When you know you have a lot of stuff that would work, but you are limited by practical constraints to smaller data collection efforts. So all subsets can be useful for that purpose. Okay, we're not going to go into any more detail than that, but I just wanted you to be aware of it in case you had ever thought that you wanted to use Stepwise because you don't want to use Stepwise. All right. Comparison of incremental and nested models. We actually use the ANOVA command for this because fundamentally a comparison of two R squareds is an F. That's basically an ANOVA. So what you do is you create your two linear models and then you put them step by step into the ANOVA command. So let's say we have, let's go back to our model. Which one do I want? Let's do, we'll just start with that one. Let's say I wanted to see, does the interaction of C and E add more beyond C and E alone? I can create model 1 and then model 2, and I could use star notation, or I could use the C colon E here if I wanted. And then ANOVA, model 1, model 2. And what you would see there is the F statistic associated with the change from model 1 to model 2. So we end up with an F of 2.572. This is not statistically significant, which means that there is no evidence here of an interaction between the two, which means we would probably retain the simpler model, right? So this is how you pull that out. But again, if you want the R squareds, you need to get them manually. So we might do summary of model 1 R, is that right? Yes. Summary of model 1, or actually not model 1, model 2. 2R squared minus summary of model 1 R squared. And there's your delta R squared. So obviously that's a very small number, so that's why there's not really an effect. So we have a very, less than 1%, actually much less than 1%, about 0.1% increase as a result of including the interaction term. Okay? Everybody follow what I just did? Yes, mostly. Okay. So again, two things. I basically just specify the model I want, the smaller model, because this is only for nested model comparisons. The smaller model here, which is C and E, and the larger model here, which is C, E, and the interaction between C and E. And I could have easily typed that instead. Same thing. No difference whatsoever. And then I used ANOVA to get the F associated with that model change, and then I ended up with that value there. And you can see the 1 degree of freedom difference between the two, as you would expect, because we've added interaction terms, so there's 1 degree of freedom difference. So that is how you would do a hierarchical linear regression. Yeah. Important, again, tidy will not have that R squared in there, so don't look for it. You got to get it manually. For relative importance modeling, have you covered relative importance? Or like relative weights analysis or anything like that? No? Okay. It's on the newer side of analysis. If you need it, we won't talk about it in a lot of detail. The idea behind relative importance is to try to figure out within a set of regression coefficients, which of them actually has the most impact on its own, controlling for the effects of all other aspects of the model. So it's when you look at standardized coefficients, all that really does is tell you in standard deviation units. It actually doesn't account for multicollinearity in any way. So that's why if you have multicollinearity, you actually can't interpret standardized coefficients. But relative importance gets around that by decomposing the R squared into other elements to try to get the unique sort of value in a standardized way out of each part of the regression. So if you have like let's say a 5 predictor regression, you can actually, and they're all correlated, you have multicollinearity issues, you can actually decompose, well, even given those multicollinearity issues, which of these is the most important predictor. And there's a lot of different theories as to how to do that. So that's why there's different like approaches listed here between LMD and Pratt and Carr and Genesi. So if that's something of interest to you, you can find it in this Rela Impo library. We're not going to talk about it in any more detail in here, but I just wanted you to be aware of it in case you need this kind of thing. Really most valuable if you're doing measurement studies, if you're doing non-experimental, like big surveys. This actually, it has in business world, this is sometimes called key drivers analysis. It's a way to figure out what like the most important aspects of a model might be. So you might use it for that purpose. But I just want you to be aware of it. We're not going to go into detail. All right. So that's all linear model, general linear model. We also have the generalized linear model, which broadens it to allow these so-called link functions in order to model DVs that do not meet the traditional assumptions of linear models. You can actually use the GLM command, which is for the generalized linear models, to do general linear model Gaussian regression. You just have to specify family equals Gaussian. It's the same thing. You won't have any different result whatsoever. However, if you want to do it a different way, if you want to do binomial, which is really logit regression, if you want to do Poisson for count data, or if you want to do gamma, if you have something that you want to model with a chi-square distribution, essentially, you can do all of those distributions using formula, comma, family equals one of those words. So if you can put in binomial, Gaussian, Poisson, or gamma capitalized, and you will get that whole piece. If you do that, actually, let's go ahead and run one. I'll take that back. We're going to create a new non-linear, what am I going to call it? Binomial model. There we go. No crazy acronym on that one. But call it binomial model. I'm going to use GLM, and this time I'm going to predict gender from OCE. It's just predicted from everything. There, done. Data equals my BFI. And we get summary of the model. And there you can see the whole thing. Oh, I've talked about that before. We saw it several times. Again, that notation right there just means all other variables when I put that dot there. Okay? But it doesn't do any interactions. It only does main effects. So just in case you didn't notice what I just did. So in this case, we're going to end up with values that are not quite right because I didn't specify what family of test this is. If I specify family is, GLM, that's what I needed. There we go. When I pull this out, you will notice there is no R squared. If you remember your logistic regression instruction, and you talked about logistic regression, right? Yes, okay, great. So when you talked about that, you probably discussed why you can't calculate R squareds in this situation. So instead, it's common to report what's called a pseudo R squared or a Nagelkirk R squared. In order to do that, you can use this library, FMSB, and use the Nagelkirk R2 command. If I do FMSB, and then Nagelkirk R squared on B model, then it just spits it back out at you. So then you're done. So if you need to get your kind of pseudo R squared, that's that value right there. Do remember it's not actually an R squared, though, of course. That number will never reach 1 and cannot reach 1 because it is not really an R squared. But it's sort of equivalent, at least close enough that people can interpret it a little more easily. Visualization's a little more complicated if you want to do visualization of this kind of model because you have to use the GLM fitted values in order to graph it. So in this case, and there was an example of this, I'm pretty sure, in DataCamp, you can use geom smooth, feed it method GLM, and this is the same notation we used last week to feed arguments into another function inside another function. We did that kind of weird like song and dance. That's all this means, is that you're running the GLM command, and then you're passing to it family equals binomial, which is really just this command up here. So what this does, what geom smooth does, it actually invokes the GLM command, and then it runs it using family equals binomial. That's all that means. So you're basically just telling geom smooth to do your legwork for you in generating a figure. The fitted values, this is the case where fitted and predicted values are different. So if you just look at the fitted values, or you look at augment without any extra parameters, it will feed you in the link values. It will feed you in the odds, the log odds, instead of giving you the actual predicted final values. So if you want to graph it on its original scale, the easiest way to do that is just to add this guy right here, type.predict equals response. Or to use the actual predict command rather than using fitted. If you need to do more advanced modeling than that, I don't know how many people in here do like crazy multi-level regression-y sort of stuff. If you need to do anything more complicated than a basic multiple regression or a basic generalized linear model using an alternative distribution of your DV, you want to use this package instead, GLM4, which gives you a lot more diagnostics and a lot more control. Or not this package, this function, a lot more control over exactly what's going on in your model. So if you're, more on the quant psyche sort of side, or you have that kind of interest, you're probably going to want to start with GLM4. You will notice you can run the same commands with GLM4, but it gives you a lot more output, like a huge amount more information, and there's also a lot more stuff you can do with it. So if you're doing things like defining slope parameters within your regression models, or you want to do things like incorporate cross-level interactions in a regression model, all that kind of multi-level stuff, you're going to want to turn to GLM4 instead, because you'll hit some roadblocks with GLM if you go too far into that. But again, not everybody needs that sort of thing, so we're not going to talk about it in here, but that's just for your awareness. If you need that kind of thing, it's in there. All right, last thing that we're going to talk about is new McGritter. So, there's actually a bunch of different pipe functions in McGritter. There's one new one I'm going to introduce today that's a little bit useful for some of the things that you're going to start to be doing, which is called explode. It is written like this. You remember that the normal forward pipe has a greater than sign there. It's just percent greater than percent. $% is explode. What explode does is it takes the names of the variables on the left side inside the data frame and just turns them into variables. So right here, this first command, or this first example, sat.act, that's another data set from Psych. Say we wanted to look at the correlation between SATV and SATQ for people that were age 18. So intuitively, I think you would do something like this. Equals 18, and we're going to pipe to correlation, SATV, SATQ, and use equals complete. Why doesn't that work? Yeah?
Because the data frame is being passed as an argument to correlation.
So remember what's really happening. Always important to decompose it to figure out what's happening under the hood. This is becoming the first parameter in the filter command, right? So this is really filter parentheses sat.act comma age equals 18. That creates a new tibble, and then that tibble becomes the first parameter of this command. So what this really is doing is core parentheses tibble comma SATV comma SATV. That is not what you want. That doesn't make any sense. But that's why it doesn't work, because it says object SATQ not found, because there shouldn't be a third parameter to core. That's why it's getting that error. So to get around that, you use explode. What explode does is instead of, I need a library McGritter. Instead of passing the entire thing back, now every variable inside sat.act is a variable. It becomes the name of a thing. And those get all passed individually to the next command. So in this case, I have sat.act. I run filter sat.act comma age equals 18, and I have a tibble. Then I hit explode, and that means that every variable in that final tibble is now available as a vector for this command. So remember earlier I talked about why it's so important to know what's in tidyverse and what's not. This is why. Because you can pass things between tidyverse and non-tidyverse, but you have to be aware of doing it. So in this case, I would not be, if I just pass this as a tibble, I would have to use, I couldn't do anything here because this tibble has no name, this tibble that's coming first. So there's no way to refer to individual variables in that tibble within a pipe. I could go around that by doing something like this. I could say new gets, and then I could do core new SATQ new SATV. But that's two, and I'd have to do use equals complete. But that's two steps when instead I could have just done that in one step. So that's just a way to clean up code if you are interested in doing that. And as you start working more and more R, you will start to want to be more and more concise in what you're writing because it's easier to read, mostly. But there are actually four different McGritter commands, so we've now covered two of them. We may or may not introduce a third, and we probably won't introduce the fourth. But if you are interested in this kind of like saving space stuff, I would recommend that you read the McGritter notation on it. So that's that. So summary of things that we talked about. Most of the time we were still talking about this guy, base R stats. Like you don't need anything special to do covariances and fitteds and coefficients predicted in ANOVA. Do note, however, this is a different ANOVA than the second ANOVA we used last time. That ANOVA was capitalized. That ANOVA is in car. That ANOVA is not the same as this ANOVA. So when you run AOV, what you're actually doing is running this command with a whole bunch of presets. That's what AOV does. It's a wrapper around ANOVA. And when you run capital A ANOVA, that is actually a completely different command from car that wraps around this to enable you to do the type 2 and type 3 sums of squares and a few other things too. So don't confuse them. They give you very different results. But if you need things this time, again, the same basic process as before. Read the earlier sections, figure out what function you need, then figure out from this list or that page where that function is, and then use that library kind of one at a time. Next week, we are getting into our first true data science stuff. As I mentioned last week, we're going to slow down a bit. So we're going to move down to a kind of a one course a week approach because it will be a different way of thinking about stuff. The first of these, we're going to ease into it using a system called R Markdown. What R Markdown allows you to do is create interactive R code on the internet so that people can poke around in data, so that you can give real-time data displays, so that you can do some really cool stuff if you want to. If you've ever been in an R-based application where you could like sometimes there's like power calculating apps on the internet, there's stuff like that. Sometimes those have R actually running under the hood, and the way they do that is with the kind of interfaces that we're going to explore next week.